Hello, this is Mr. Collier, and today we're doing rational functions, which means ratio functions, but more specifically just linear functions like these. Okay, so let's sketch 1 over x, and if you want to know what a function looks like, you can just substitute in values of x and get some points. So 1 is a nice one to sub in. You sub in 1, you get 0, and you sub in 2, you get half. If you sub in a number like half, 1 divided by half is 2. Now the numbers get smaller and smaller and smaller this way. They approach 0 as x goes to infinity. So this is an asymptote here. And your function goes like this. Well, that's a bad drawing. Let me try that a bit closer. So you should be closer and closer to that asymptote, and if you do 1 divided by 0, it's undefined, or if you do 1 divided by a really small number, you're going off to infinity. So it looks like this, and we have a vertical asymptote. So if it's a linear rational function, you always get two asymptotes, one vertical, one horizontal. Okay, now if you substitute negative numbers in, you get the same kind of graph, but over here, right? 1 divided by negative 1 is negative 1, 1 divided by negative half is 2, and negative 2, and so forth. So you get this mirror image here, and the shape is called a hyperbola. Okay, so you get these asymptotes. In this case, there's no intercepts. But this, well, you can sub in points, but we know this is translation, because it's x minus 3 translation, 3 right, and 1 up. So the whole thing moves 3 right and 1 up. Every point moves 1, 2, 3 right and 1 up. The same thing with the asymptotes. So the asymptote is now going to be up here at y equals 1, and the vertical asymptote is moved to the right 3. It's going to be at x equals 3, and you got the same shape, but it's over here. Okay, in this case you get some axes intercepts too, an x-intercept and a y-intercept. Okay, let's check out the next question. Looking at horizontal asymptotes, use technology to graph the rational functions. Okay. So, yeah, let's take a look at this one here. Let's graph it. Now it's not so straightforward as the ones above. Let's graph them in decimals. 2x minus 3. So let's get 2x minus 3. Y equals 2x minus 3. Actually, let me do that. Two x minus 3 and x plus 1. Okay, so we get this shape. We see there's a vertical asymptote at negative 1, which makes sense. Because if you sub in negative 1 here, you get divided by 0. That gives you a vertical asymptote. And you get a horizontal asymptote at what looks like y equals 2. Okay, so if we look at, well, the 1 is kind of obvious. We have a vertical asymptote at x equals negative 1. The vertical asymptote, or the horizontal asymptote is y equals 2, and that's actually just the ratio of these coefficients, and we'll see why in a second. So we got y equals 2, x equals negative 1, and you're going to get this shape right here. Okay, the reason is the horizontal asymptotes occur as x goes to infinity or negative infinity, right? So let me introduce you to the concept of the limit. The limit is a number that x approaches, or the function approaches, as x goes to infinity, or you could say to negative infinity as well, right? So when x goes to infinity, if you look at the function, the negative 3 and the 1 don't matter, because if you've got 2 million minus 3 divided by 1 million plus 1 is practically still 2. It's very, very close to 2. Okay, so for very high values of, or large values of x, this quantity is very, very, very close to 2. So the y values are getting very closer and closer to 2. Okay, so it's just a ratio of these coefficients for a linear rational function. Okay, so you should be able to just look at the function and figure out what the horizontal asymptote is. Okay, here, the vertical asymptote is just when the denominator equals 0. Okay, it's because dividing by 0 is undefined and it creates that, so you get cx equals negative d, x equals negative d over c. Horizontal asymptote is the ratio, as well as y equals the ratio of these coefficients, a over c plus f. Okay, because as x gets infinitely large, the b and the d don't matter. This quantity simplifies to approximately a over c, and then you add the f, and that's the way it always works, right? So let's do a graph here, one full graph. So we can see the vertical asymptote is going to be when the denominator equals 0. Okay, we got x equals half. Should always label the asymptotes as an equation. And the horizontal asymptote is the ratio of these coefficients of x. So y equals negative 3 over 2, or about 1.5. Label it. There's going to be some intercepts. The x-intercept happens when y equals 0. Now for these rational functions, this can only be 0 if the numerator equals 0. So 3x equals negative 2, x equals negative 2/3. That's between 0 and 1. Perhaps I should have used a different color. And the y-intercept happens when x equals 0. So that is 2. Okay, or is that negative 2? That doesn't look like it's going to be at 2, is it? Okay, 1, 2. Okay, that kind of doesn't make sense. So let's check that again. Here we've got the horizontal asymptote is wrong. It's negative 1.5, sorry. Negative 1.5, now it makes sense. Alright, so then you've got, it's a little bit hard to see there, but that's the y-intercept, so it goes up like this, and then it's going to be the same shape on the other side. Okay, let's take a look at some more examples so you can get the equation of this here function by looking at the vertical and horizontal asymptotes. Looks like a horizontal asymptote right there at negative 3. And a vertical asymptote at 2. Okay, so we have that. So your function might be, well, one way to do it is to just do x minus 2 in the denominator, and your numerator you have negative 3x. That will give you this, right? But then it might not match some of these points. So I'm going to put in a plus b. Alright, and then we're going to use a point, maybe the y-intercept, to figure out that's 0, negative 2 is the y-intercept. So let's sub that in. Let's sub in 0, negative 2. Then we have negative 2 equals 3 times 0 plus b over 0 minus 2. So we get 4 equals b. So the function is negative 3x plus 4 over x minus 2. Let's check it out in Desmos and see if that looks right. Okay, so what did I say? Negative 3x plus 4. Over x minus 2. Okay, so this, you see this totally matches the graph from the example. Okay, let's take a look at another example now, one more example. Let's talk about the domain and range of these functions. I should have been talking about them a bit before. Actually, maybe, okay, let's just do it for this one. So here we have, actually let's talk about the horizontal and vertical asymptote. The vertical asymptote is x equals 2, and the horizontal asymptote, now this is like 0x plus 1, so this whole quantity is going to be close to 0 as x goes to infinity, so your horizontal asymptote is y equals 3. Okay, so your domain range is always based on this. This is x can be any real number, except it can't be 2. And y can be any real number except 3. Okay, so domain range is always like just one exception value. Find the inverse. Okay, so we just swap the x and the y. X equals 1 over y minus 2 plus 3. What's the best way to solve this? I guess x minus 3 equals 1 over y minus 2. You can multiply here both sides, but you actually flip both sides. So f inverse of x, you should always use this notation at the end, is 1 over x minus 3 plus 2. Okay, now part B is to verify that it is the inverse. So you do f inverse of f of x. That means you take f of x and put it into the inverse. So 1 over x minus 3 plus 2, but your x is the f of x, which is that a 1? Yes, 1 over x minus 2 plus 3. Okay, so when we simplify that, these 3's cancel, you just get x minus 2 plus 2, which equals x. So that verifies that it is an inverse. The domain range of the inverse, well, that's just the same as the range and domain of the original function. So this should be x is all real numbers except 2, right? And that makes sense by looking at this. And your range, actually 3, sorry. Swap it around. 2, 3 should become 3, 2. Y is all real numbers except 2. Okay, that makes sense because you got 3 down here. Solve the equation f inverse of x equals f of x. Well, we can set them equal to each other. But actually, any function and its inverse are reflected over y equals x. So if you've got a function and its inverse, it's going to always meet on the line y equals x. So this is the same as just setting x equal to either of the functions. So they both look about the same difficulty to solve. So you can just set it equal to this, because y equals x, the inverse and the function all meet on the same line. So we can just solve this equation. Okay, so let's solve that. I'm just going to do x minus 3 equals 1 over x minus 2, and then we're going to multiply and multiply these together. Get a quadratic x squared minus 3x minus 2x plus 6 equals 1. So we got x squared minus 5x plus 5 equals 0. And then solve that equation, which involves quadratic formula.